Welcome to the AP Physics Kinematics problem set, the solutions for number 18 and 19. Let's jump right in with number 18 here. A ball is thrown vertically upward with a speed of 25 meters per second. This would be its initial velocity directed up. We're going to come over here and we're going to draw a quick little diagram and label some other information. This really is the first assignment in which we switch planes here. We've been doing motion problems in the horizontal plane. Here is our first motion problem in the vertical plane. We call them one-dimensional free fall problems. So here we have a soccer ball that's going to travel upward and come to rest at the peak of its flight. And as mentioned, we have been given its initial velocity of 25 meters per second. What else do we know? We know at the peak of the flight that the velocity, the final velocity at the top is 0. And we know that gravity acts on it, and because of that it has an acceleration due to gravity, and the symbol for that is little g. And because it's in the opposite direction of the motion, we would say that it's negative 9.8 meters per second squared. Okay? Our first question, how high does it rise? Okay? And that would be x. So they want us to find the x value. B, how long did it take? That, of course, is time. So they also want us to find the time that it takes to get to the top. And then C, how long does it take the ball to hit the ground after it reaches the highest point? And D, what is its velocity when it returns to the level from which it started? We'll address those when we get to them. For A, how high does it rise? So we're looking for X. We have VO, we know V, and we know A. Sounds like we should use, if we go to our reference table and inspect, V squared equals VO squared plus 2AX. And what we can do in these problems is change the A to a G. 0 squared equals 25 squared plus 2 times negative 9.8 times X. Take whatever algebra steps you need to solve for X. Pause the video if needed. Do the calculation. And we get 31.9 meters to 3 digits. And that's our answer to A. For B, how long did it take? We're looking for the time. We have VO, V, and A, so it looks like we could use V equals VO plus AT. Once again, we can change the A to a G. 0 equals 25 plus negative 9.8 times T. Solve for T. Go ahead and do your calculation. 2.55 seconds. So that's our answer to B. C, how long does it take the ball to hit the ground after it reaches the highest point? And perhaps it's intuitive that the amount of time it takes for the ball to rise has got to be the same as the amount of time for the ball to fall. Acceleration due to gravity is constant. It acts equally on the object at all times. So if it took 2.55 seconds for the ball to rise, then it's going to accelerate downward at the same rate at which it was slowed down. So the answer is 2.55 seconds for the ball to fall back to the ground. D, what is its velocity when it returns to the level from which it started? Well, it's going to start from rest. It's going to be accelerated due to gravity at 9.8 meters per second squared for 2.55 seconds. We can see this is just the reverse of the answer for B. So we understand intuitively also that our speed at the bottom is going to be back to 25 meters per second. Okay? All right, let's move on to 19. A small mailbag is released from a helicopter that is descending steadily at 1.5 meters per second. So we go ahead, and we know that's velocity. After 2 seconds, and they gave us time, what is the speed of the mailbag? So we come back, we now recognize that the 1.50 meters per second is initial velocity. The speed of the mailbag is its final velocity. How far is it below the helicopter? Okay, and that's x. And what are your answers to A and B if the helicopter is rising steadily 1.5 meters per second instead of descending? Okay, let's start by labeling the diagram here. We're going to do a label for the mailbag. We have the mailbag descending at a VO of negative 1.50 meters per second. What we're doing here is we're designating the direction down to be negative and the direction up to be positive. We're doing that because of C. In reality, if all we had to do is A and B in this question, we wouldn't have to do that. But at some point, the helicopter is going to be rising, as mentioned in C. So I'm just taking care of this up front. We know that our time is 2 seconds. And we know that the mailbag is accelerating due to gravity at negative 9.8 meters per second squared. So here's additional information. Whenever there's a free fall problem, we know that it's accelerating due to gravity. Okay? All right, so for A, what is the speed of the mailbag? Well, we have looking for the final velocity, and we have initial time and acceleration. V equals VO plus AT. Okay, and we'll change the A to a G. V equals negative 1.5 plus negative 9.8 times T times 2. The final velocity, if we go ahead and calculate that, is negative 21.1 meters per second. What does that tell us? It tells us, of course, that after 2 seconds, the bag is still falling downward, which makes sense given the problem. Okay? For B, how far is it below the helicopter? Well, we're looking for x. We know its initial velocity, time, and acceleration. We go to the reference table. Looks like a good choice would be x equals VOT plus 1/2 AT squared. Again, changing the A to a G. Go ahead and substitute negative 1.50 times 2 plus 1/2 times negative 9.8 times 2 squared. Go ahead and calculate x, and we get a value negative 22.6 meters. However, the question did not ask how far has the bag fallen, which is what the answer so far is to be. It says how far is it below the helicopter. Well, the key here in B is that while the bag is falling, the helicopter is also descending at 1.50 meters per second. Okay? So we need to take that in consideration as well. So the next piece that we're going to do here is find out how far has the helicopter descended while the bag has been falling. The helicopter is not accelerating downward due to gravity, it's just descending at a constant speed of 1.50 meters per second. So in this case, since it's not accelerating, V equals x over t. It's descending at negative 1.5 meters per second for 2 seconds. So it has fallen 3 meters. It has descended 3 meters. Let's go back over to our diagram here. So our bag, from the point of its drop, and we'll draw that from the helicopter, our bag has fallen 22, get a little clearer there, 22.6 meters. Meanwhile, the helicopter has descended 3 meters. Now we employ common sense. How will we get how far below the helicopter the bag is? It looks simply from our diagram like we would subtract those two values. So our final answer, x, is going to be the 22.6 minus the 3 meters the helicopter has descended, to be an answer that's 19.6 meters below the helicopter. Okay, that's our answer to B. In C, they want us to repeat these calculations for the case in which the helicopter is ascending, rising at 1.5. So let's go ahead and kind of start over here with a fresh diagram. This time, our bag, upon release, is ascending. So it's a positive 1.50 meters per second. All the rest of the information is the same as it was before. The time is still 2 seconds. And the acceleration is due to gravity at negative 9.8 meters per second squared. You can see here now where sign is really important, because the initial velocity is upward while the acceleration due to gravity is acting downward. Those are conflicting directions, so we need to have sign that represents that appropriately. Okay? All right, so back to our speed after 2 seconds. Same equation, v equals VO plus GT. I'm just going to shortcut to that. V equals positive 1.5 plus negative 9.8 times 2. Solve for V, and we get negative 18.1 meters per second. Now, what this indicates to us is that after 2 seconds, the bag is falling because its velocity is in the negative direction. All right, now we're going to go ahead and do the distance part, repeating the same. X equals VOT plus 1/2 GT squared. Positive 1.5 times 2 plus 1/2 negative 9.8 times 2 squared. So X equals, go ahead and do the math on that, negative 16.6 meters. And again, what we have to remember is that's how far the bag has fallen from its release point. So if we call the helicopter up here in our diagram the release point, the bag from that moment is 16.6 meters below where it was released from. Okay? What's happened in the meantime? In the meantime, the helicopter has risen at 1.5 meters per second. So again, V equals X over T. 1.5 equals X over 2. So X equals 3 meters. So pretty clear that the helicopter has risen 3 meters while the bag's displacement after 2 seconds is 16.6 meters below the spot it was released. So how do we find the overall distance between the helicopter and the bag? It should be obvious to us from our diagram that we're going to add those two values. So our final X answer is 16.6 plus 3, which is 19.6 meters below the helicopter. And what's really cool about this, gotta love physics, is the answers to the first part where the helicopter was descending and the answer to the second part where the helicopter was ascending are identical with regards to the position. All right, so tomorrow in class we'll be doing number 20, and so more practice on one-dimensional free fall.